Hello and welcome to my channel Deep Linux. In this video and a series of video that will follow this one, I'm going to talk about some of the essential techniques that I've used to create the content in this channel. Now, specifically speaking, I'm going to be talking about tracing and the different kinds of tracing that we have and when and why they would be useful and the tools that you would use for tracing and comparing tracing with logging. What do I mean by tracing? By tracing, I mean intercepting and recording events that are a result of code execution. So we have basically code, and this is the code, and we're executing code. And so So what happens is that when the code is executing, we can insert instrumentation points, okay? And so this is like an instrumentation point that when hit would produce an event, which would tell us, oh, you're executing this line of code and these are the parameters and whatnot, okay? And then you would store these events in like a buffer, for instance. So you would have like a buffer, and then you would put events here, event 2, event 3, so on and so forth. So this is what I mean by tracing. Now, this code can be user space code, or it could be kernel code. All are possible. And there are many different mechanisms for putting these instrumentations in, right? We have kprobes and uprobes. Kprobes are for kernel, uprobes for user space. We have something called trace points, and um, you know we have, let's say, eBPF and so on and so forth. Okay. So this is tracing, but why would you want to do tracing? Why? Well, there are different reasons here. You may want to debug the code. You may want to debug your code. You may want to know the performance. So for instance, some latency, right, between two different points. So you would intercept event 1 and then intercept event 2 and then compute the latency between these two and to know what's the performance or various other performance measures for that matter. The other reason is you want to understand code. So you just want to understand what's going on. Because why would you want to do that? Well, for several reasons. Let's say you want to add a feature to your code, but you don't understand how the code works originally to begin with. So you first need to understand the code, and that's one very effective way to do that is to do tracing. Okay, so it's usually either troubleshooting, performance reasons, or understanding the code. Now, there's another question here. Now, you probably all know about the logging, like logging in software in general. Like in Linux kernel, you have logs, right? Systemd has logs, and journald has logs, and you name it. A lot of the softwares that people write have logs, right? And so, what's the difference between logging and tracing? So, why all of a sudden we need tracing? Why can't we just use logging? So that's actually a good question. So let's look at that question. Well, logging is, well, we have the most famous one is syslog. These are logs generated in Linux um, by applications that are put in the syslog and under var log messages, for instance. We have kernel logs. Um, which using the dmessage command, you can actually look at the kernel logs. Now, for instance, let's just have a look at these. So if I say dmessage and then go tail to look at the last few of these are kernel logs, right? Okay, so USB product Jabra evolve, so on and so forth. This was plugged in and input my pen pad, right? All sorts of things like the events that happen in the kernel. Why do we need tracing? Now, the answer is several things. So first off, logging, the delays in logging, well, actually, let's start with this one. Logging is writes to disk, okay? So you need to write to the disk. Logs go to the disk, whereas tracing doesn't necessarily go to the disk. You write to RAM. So you write to a RAM buffer. Well, you could also choose to dump the RAM buffer to the disk, and this is what we usually do, but we don't have to do that, right? But logs always go to the disk. So that means that logging would be a blocking operation. To write the log, it would be a blocking operation. What it also means is that you would require a mode switch or like a kernel, it's a kernel space operation, or I would say a kernel switch, which means that you would have to switch to kernel mode. Here, you do not require. You can do it in user space, and you can do it in kernel space without having to actually do a context switch. Okay, so again, it's more performance tracing. It is more performance. The other thing is that logging is usually in it's in the microsecond to millisecond range. Let's say hundreds of microseconds to 1 millisecond, right? In that range, the overhead. But in tracing, it's usually in the nanosecond to low microsecond range, right? So it's like 2 orders of magnitude at least faster. The other thing is that in logging, you usually have coarse grain, coarse resolution, uh, but in tracing you have fine resolution. So essentially, uh, you can trace instruction by instruction. We don't suggest that you do that because of the overhead, but you could. If you wanted to, you could. So these are some of the comparisons, and that's why logging and tracing solve different problems. So one is not there to replace the other, but definitely you have to make sure that you don't use logging instead of tracing and vice versa. Okay. So logging is essentially to record software execution health or important events that would then help to troubleshoot, right? On a normal day, basically, when everything is okay, you would use logging, okay? Uh, and it has some performance impact, so you don't want to log extensively. Logging is something that's always on, usually, so you're in that mode of operation. But tracing is something that is usually done when something is wrong or when you're doing some development, troubleshooting, debugging, performance evaluation, whatnot, right? So it tends to be not always on, but I've seen cases that it made complete sense to have tracing always on, albeit with a limited amount of tracing. Now, so you would use tracing when you want to drill down on something, right? When you want to get a lot of fine resolution information about what's going on in the system. So I would say the scope of tracing is quite targeted, right? And it's not that, oh, you want to, basically report the detected errors in the software or whatnot, right? There is a more of a like a debug mode of operation to it, okay? So one is not going to replace the other. Now, having said that, what I'm going to do in this video is start to explain about the different kinds of tracing that we would do and which um, tracing strategy is best in which type of problems. So I'll just give an overview in this video, and then in the next videos, I will go through different tools that are designed as front end or let's say back end for tracing, well, mostly front end, I would say, um, for tracing, and then explain how they work. And basically, these are going to be tutorials, although these tutorials are out there in the internet as well. But what I'm going to do is I'm going to keep it like concise and down to the point, so that you can actually start off doing things on your own fairly quickly. Okay, now the um, probably easiest kind of tracing, or let's say the most normal and straightforward kind of tracing, is simply event tracing, where you would record the events that are happening with their timestamps. Okay, so let me give you an example of this event tracing here. This is basically an event trace. So let's just go bring it to the side, and you can see that. Okay, this is actually an event trace that is gathered by a tool called ftrace, which is built into the kernel. Now, this in ftrace jargon, this is known as the NOP, or no operation tracer. You can see that these are events here. You'll see the event name, you'll see the task, you'll see a timestamp on which CPU the event happened, what task or thread was running at the time, and the event parameters. Basically, these are the event arguments and parameters, okay? And there may be a bunch of other useful information depending on the tracing tool that you're using in this case, which is ftrace. So this is what's called an event trace. So you can see that these are events, 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 right? This is one type of doing tracing. Now, the other kind of tracing is where you actually, and by the way, these are actually events that are predefined in the kernel. So they have a stable API, meaning that the event and the parameters don't change. At least they're not supposed to change that much. So event tracing is basically, you can either trace with this, you can trace trace points, which is what you see here, or you can trace any instruction, pretty much. In kernel space, this can be done with kprobes. I won't show you the how, but I'm just going to tell you what we have. In user space, you can put uprobes on any instruction pretty much, and trigger an event based on top of that. So trace points have a stable API, meaning that from kernel to kernel, they don't change. They're always there with that same definition. Uh, but if you want to be able to do tracing on any instruction, then if it's in the kernel space, you have to enable a kprobe on that instruction. If it's in user space, you have to enable a uprobe on that instruction, and then this instruction can as well be a function, a function call, right? So we're going to get into the details of this in the next videos in this series, but just we're touching on the important points here. So that's event tracing. This, what you see here, is event tracing. But let's say I want to, you know, trace all the functions, right? So event is not necessarily um, a a function call. So let me show what let me show you what an event is. I'm just going to bring up the kernel code here, and so this is the kernel code. Let's just zoom it up a little bit. Okay, so say looking for trace. Actually, let's pick one of these guys that we had already here. Yeah, this guy. So sketch switch, for instance, this is an event. Okay, sketch switch. It's an event. And what I want to do is, so I want to find the trace point, trace sketch switch, and voila. Here, you can see that inside the kernel code here in this function here inside the kernel code, this trace point has been called. Okay, this is actually a macro. There's a lot of piping, going into this and how this actually triggers the event, right? If the event is enabled, by the way. But that's a lot of advanced stuff that you don't want to know about necessarily, unless you are kernel, like you're a kernel developer working in the developing the tracing internals, right? So you don't even have to know how this whole thing works internally if you just want to write new trace points. That's relatively easy to do. So when you say trace sketch event, sketch switch, this is basically here. Whenever the kernel code hits this point, it's going to generate that event for you with the timestamp and on what CPU and what task was running when this happened on that CPU and so on and so forth, right? With all the parameters here, right? That are essentially passed, you know, using these parameters are passed to that trace point. So not getting into a lot of detail again, but this is how these trace points are triggered. So these are the trace points part, right? These are trace points. Now, sometimes I want to trace the functions. So let's say this function that this trace point is in, uh, this function, right? Schedule. Of course, this function is not supposed to be traced, but let's just pick some function. Let's assume that this function entry point, sorry, can be traced, right? And I want to function, and I want to trace this function, or I just want to trace this function, or I want to trace this function, some function, right? What if I want to trace those functions, the entry and exit into and out of those functions? Then, I'm not essentially, I'm not going to be doing event tracing. What I'm going to be doing in that case is I'm going to be doing what we call function tracing. Now, function tracing, what it does is that it basically traces function entry and exit. And the mechanism for this is that they kind of there are several different mechanisms for this. So essentially, a common mechanism is that they put like a bunch of NOP operations, assembly operations at the function entry point, and then whenever you enable that function and tracing on that function, those NOPs are overwritten with a function call that actually calls a trampoline or jumps into a trampoline, and that function call is the code that would produce the event for you. So it's a little bit involved, but anyways, that's what we call the function tracing. And let me show you an example of function tracing. So let's see a case of that. Okay, so this is actually an example of a function trace collected by the ftrace tracer again. So you can see here that this function is being called. So this only shows you the function entry, by the way. And this function is being called, this function, this function. So these are the functions that are being called. And here it shows you which function called which function. So this function is called by that function and so on and so forth. So this is if you want to trace the function execution as opposed to, certain points in the code. Now, the other way, like these actually increase in terms of complexity, right? Or let's say in terms of detail and the kind of fine resolution debugging that you're doing. The other kind of tracing is called function graph tracing. So it's a function graph tracing. And what that means is that it will show you the sequence of function executions from entry to exit, right? So let me show you by an example here. This is a function graph tracing collected by the ftrace tracer. And you can see that it tells you that this function netrx action is being called. This is collected from the kernel, which then calls this function, and then this calls this function, which then this function API poll calls these guys, and so on and so forth. And at the end, somewhere it has to kind of return. Sorry, right? That's when things finish. So this is what we call a function graph tracing. This is the most like most fine resolution tracing and that you could do, right? I'll take my word with a grain of salt, of course. Um, and then here's is when we really want to drill down and see what is happening in the code. Okay, so this is function graph tracing. Now, another type of tracing. Now, these tracings kind of increase in terms of complexity and overhead. They tend to be like that, not necessarily, but essentially, it's more and more events, right? If like all other things being the same, it's much more. There's much more overhead in creating a function graph of every function that's traced compared to just functions that like this function is called, this function that's set. So and compared to event tracing, right? But let me also introduce some very low impact, actually. So it kind of breaks the order here. A very low impact kind of tracing, which is called statistical tracing. So I would say stats or counts, if you may. And this will just give you the count for the number of events that have happened of any event type of interest, or let's say the functions that have been called. So as an example, here, actually, no, this is a better example here. So uh, this is basically so for a certain number of events here, right, we can see that the event has been triggered this many time and this much and this much and so on and so forth. And you can either generate these for the events, for like the stable API events, for any K probes that you define, for any U probe that you define, for any function that you desire, so you can get these counts for anything that you want, right? In this case, it's these counts are generated only for the events that are in the kernel space, but it doesn't mean that you could do it for K probes or U probes, right? So here you like this is very low impact because you're not really generating some event and putting it in like a buffer. Um, you're just incrementing a counter, and that's very fast. This is usually done when you want to understand which part of the code is being impacted by a certain test case or a certain condition. This is a very powerful technique that I've talked about in my channel. It's very powerful, and you can use it to identify the um, the hotspots, the um, where you have to do your feature work, or let's say where the whereabouts of the root cause, of the issue that you're investigating, or what is the high runner in terms of the performance problem that you're dealing with, right? What are the top few places that you have to look for to kind of drill down what your performance bottleneck is from, right? So this is the stats and count tracing. Now, we also have another mode of tracing, and not going to call this tracing. I'm just going to call it profiling. Okay. So actually, before going to profiling, I'm also going to talk about performance counters or performance monitoring counters, or what we call PMC sometimes, PMC tracing or performance monitoring counter tracing. Um, these are um, these are very similar to stats counting, but I'm separating them because they refer to some intrinsic hardware events, such as CPU cycles, for instance. So where do most of my CPU cycles go, or how many CPU cycles have I executed? Um, the let's say cache misses, um, page faults, and they're not necessarily hardware all the time, but you know most of them are, and so on and so forth, right? So you could also trace these ones. Let me show you a case here. So for instance, this is a performance counter statistics that we've gathered, and it shows us how many CPU clocks and how many context switches and how many CPU migrations, how many page faults, and how many CPU cycles, how many instructions, branches, branch misses, so on and so forth, right? In this case, we don't have the cache miss hit rate, right? But those could be there as well. So these are very interesting things to be monitoring. Um, so those are also performance monitoring counters. Now we also have another thing called profiling. Now profiling, some people don't like to relate tracing to profiling. They like to view them as separate things. I personally don't really care that much, but usually in profiling, the target is looking at the code hotspots. You want to know where is the most CPU or the most something page fault or the most cache miss, whatever, right, is happening in your code. And you could actually, so, you could relate it to, you could say it's a different kind of tracing or it's not, right? Uh, in my view, it's again another type of tracing done for different purpose, right? So in profiling, you want to know what are the code hotspots usually. So it's not for debugging, it's more for performance reasons. Um, so profiling is basically you have events, is something that is event triggered, right? Let's say, what do I mean by that? Like, I want to know, uh, like when I'm getting these page faults. Like it could be triggered by page faults, for instance, or it could be just periodically triggered, right? Periodic, right? You just take like, periodically take a snapshot of what instruction is running on the CPU to basically kind of characterize the workload that you have and say, okay, you know what, actually this part of my code is using 70% of my CPU. So let's do an optimization there, right? So this is what profiling is. It's either like event triggered or it's periodic, right? And whatever that is, what you want to do is you want to collect some information. So the information that you collect, the info that you collect is either the CPU instruction. Um, so what instruction was I executing? Or sometimes you collect the stack. See, basically what was on the stack that I was executing, right? And these have different, uses. So for instance, let me show you a case of where we have collected the stacks. This was collected by perf, and these are stack traces, right? Whenever there was a page fault, we took the stack. So we wanted to know what was happening, what was the application doing, the application in this case being the tar application when we got a page fault, right? So we were doing stack triggered based on event, and the event would be page fault, right? Um, yeah. And then from these, or you could actually, it doesn't have to be stack page faults. It could be anything. It could be CPU cycles. What was the CPU doing? Sorry. Uh, every few thousand, few million CPU cycles, we take a snapshot of the stack. So what's going on there, right? And then we can actually come up with something called a flame graph, which I'm going to show you. So this is a case of a flame graph that is created from those stacks. So it's actually a stack, aggregated stack, right? Um, and it's just, so these are actually stacks. And here, let's take a look at one of these, right? Um, just gonna open it with another application with Firefox. Yeah, okay. So here, I'm gonna click here, for instance. You can see, you can better see the stack, right? This is the stack. So let's say this is, there are 16 samples, with of this stack gathered, and so on and so forth, right? So this is what we call a flame graph. And by the way, the x-axis is not really time, it's just frequency. So the width of these bars are frequency, right? So we can see like the stack depth, and how relevant, like how many times when this event happened and we took a snapshot was this guy on the stack, and so on and so forth. Okay. We're all gonna, we're gonna get back to all of this, and talk about these in more detail in the next few videos. But this is just like an introduction. This is like a teaser, if you may. So that's also profiling, right? So this is pretty much conventional tracing. And then if non-conventional, let's see, a little bit of modern tracing is that when you want to do analysis along with tracing. So you're not just tracing, but you're tracing and actively analyzing the trace. In normal tracing or profiling, you just, hit a trace point, in whichever way you dump some, information such as, oh, I call this function, I triggered this event, and these are the parameters and whatnot, right? But if you, let's say, you want to say you want to know how long system calls take. So you want to trace system call entry and system call exit, but you don't want to really record all the system calls. What we just want to do is that whenever you enter the system call, set a timestamp, and then whenever you exit that system call, compute the time difference and just, sum that up, and then take an average or something to kind of understand what's your average the average time you spend in a system call, so that there's an analysis element going on there, right? You want to basically run an analysis code when you hit certain trace points or events or functions or whatnot, right? That is enabled by a very powerful technology in the Linux kernel called enhanced BPF, or sometimes even BPF for short, which stands for Berkeley Packet Filters. Now, do not let the packet term there mislead you. This doesn't necessarily have to do anything with packets, but the origins comes from the packet domain, and the need to kind of have hooks to trace packets in the kernel, right? But it's been evolved, and you can basically place a hook anywhere in the kernel and attach that hook to kind of a snippet or script that would run your analysis for you, right? So this is eBPF. It's very, very powerful. There's one video about eBPF on the channel for basically assessing the interrupt latency. Now, let me show you, some sample of what BPF can do. And there are many, many tools that are written based on BPF, right? Um, so they're like the tools are different, but the underlying backend, right, and the kernel is the same thing. This is basically tracking the latency or like the lifetime of a socket buffer inside the Linux kernel, how much time it takes for a packet to kind of, be processed through the kernel stack. And I'm just going to run it and stop it. And then you can see that this is basically telling me that, um, how much time in terms of a histogram these packets have spent in the kernel stack trying to be served, right? And then passed to the application. This is a very cool information that you have, but you would be surprised how much code it took to write this. Oh, it took this much code. Just this much code. So that's it. This is the amount of code. Nothing more. Very simple, right? So we're going to be talking about this as well. And then, of course, there's a video right now on the channel that talks about a different kind of application for this, but we're going to cover this in this series as well in a little bit more depth. Now, so this BPF is very low overhead. So the overhead is low overhead and very memory efficient because so it's both CPU and memory efficient. Um, and because you're doing the analysis, you're discarding the events that you don't want. You just keep track of a few variables, kind of. And then in terms of impact, and these are like, generally speaking, in terms of performance impact, uh, if I wanted to classify them, this would be number one, best, right? Then it would be this one, then this one, and these are two and three are very close. Um, and then I would say, I would give BPF also a two, right? It depends, right? And then this guy would be four. So this is how they kind of, compare with each other. Okay. Um, in terms of the so in terms of the information that you gather when you're doing profiling, right? The impact of profiling completely depends on the information that you gather. If it's like CPU instruction, which is just one register, which is the program counter, it's very quick. But if it's the stack, there's a lot of overhead here, right? You don't want to do a lot of stack traces. Like I would say this is probably the most overhead. Uh, this incurs the largest overhead when you're collecting traces, right? So this is the last thing you want to do. Or if you do this, you don't want to do it. You don't want to trigger too many events if you're collecting a stack, right? So have that in mind. And then there are a variety of tools out there for this. We have so in this space, let's say here. So in this space, we have something called PLY that I just showed you in the space of BPF. We have BPF trace, we have BCC, so on and so forth. Here in all of this space here, we have perf, we have LTTNG, we have ftrace, and we have kprobes and uprobes, as I said, and some other tools as well. But I would say these are the most important ones. And I'll be talking about all of these in the next videos to come. I hope you've enjoyed this, and I hope I've laid the groundwork or some, with some introductory knowledge that we could then use in the next videos to kind of understand what we're really doing in all of these cases.